the first question asks us to order the numbers from least to greatest. All right, so you're just putting it in order, but really you're looking at a mixture of rational and irrational numbers. It's a question of what is the nature of these numbers. Some of them you can figure out on the fly. Some of them you need some piece of computing to be able to handle. So this one, obvious. That one you could probably figure out. If you wrote that as a mixed number, what would it be? 3 1/3, right?
3 1/3.
Exactly. All right. That one, maybe not. Maybe you need a calculator. But I prefer to at least give it a stab when I do it by doing it in my head without going to the calculator immediately. So the first thing that I try to do when I'm dealing with radicals is try to determine what numbers it's between. All right. So, like for example, I know 3 squared is 9, 4 squared is 16. So I know it's somewhere between 3 and 4. Is it closer to 3 or is it closer to 4? Closer to 4 because 14 is closer to 16 than it is 9, right? So when you consider that, you might draw the conclusion that rad 14 is bigger than 10/3, right? Because this is closer to 3. That's 3 1/3, all right? This is right in the middle, so if you're saying this is closer to 4, that's closer to 3, then you're probably saying smallest, middle, largest, all right? I'm saying give that a shot. Try to do that. Reality is you have these calculators. And I say this all the time, especially in Regents courses, that you want to learn the math. You want to be comfortable with it. You want to draw conclusions. You want to have a deep understanding. But ultimately, at the end of the year, when you're sitting for that Regents, you want to get stuff right, right? You want to sit down, take that exam, and know that you got the question right. So 3.5, I don't have to type in. 10/3, I could type it in as a division problem, because if I type it in as a fraction, some of you might know this little trick, alpha window. Alpha y equals brings up the n over d option, n over d numerator over denominator, puts it in as a fraction. The problem with that is you're telling the calculator I'd like to work in fraction form. So it's just going to tell you, yeah, it is 10 over 3. Very good. And I'm like, well, can you tell me what that's equivalent to? So you want to put it as a division problem if you want it to be converted to a decimal. All right. But the good news is, you remember simplifying fractions? You've done that, right?
Yeah.
Middle school? It was not too bad until it was bad. Like if you had something like 25/15, you knew it was divisible top and bottom by 5. But then you got 51/17, and you're like, well, I'm not really sure about that one. So you popped it in the calculator and you saw what came up, maybe, if you were allowed to use a calculator. This is nice. Or let me do 17 over 51. Alpha y equals, type in the 17 over 51. The calculator will reduce it for you. All right. So it's a nice little feature. If you have to simplify fractions, the calculator can handle that for you. So there's some numerical things that you don't have to worry about anymore, which is really nice. All right. Because the focus of this course is algebra. Like, we're going to have to do all that stuff you learned with numbers, but with variables. So we're interested in getting bogged down with calculation, all right? The numerical stuff, numbers. We want to put that aside so we can focus on the letters, all right? Okay, so the real interesting component is what is the quality of rad 14? So the square root key, let me get my, because if you're not familiar with the calculator, you may not know that the square root key is second that x squared key. All right, so I hit second, that x squared key brings up the rad, and type in my 14, hit the right arrow to get out of the radical, and then hit enter. All right, so my suspicion was correct. Now you probably completed this problem long before I would have, with this entire explanation. You're probably done with this in like 10 seconds. But I don't know how much of that calculator stuff you knew, so I figured it was worth the time. So we conclude that, let me just do it this way, I like it this side. that the 10/3 is the smallest, the 3.5 is medium rare, and the root 14 is the well done. Now, for something like the square root of 1/4, now the other ones you're fine with, I think, because most people know that the decimal version of 1/3 is 0.3 repeat, yeah. So we know what that is. So we know that that's bigger than the 0.16 repeated, all right? Now, because 33 is bigger than 16. It's the question of this guy. Now that's where you want to focus your attention, but the process is very simple, as long as you know that when you're taking the square root of a fraction, you're taking the square root of the top and the bottom separately from one another. All right? So the square root of 1 is 1. The square root of 4 is
2.
The decimal form of which is 0.5. All right? So we now know the ordering of this. We know we're looking at 0.16 repeated, 1/3, the biggest one being the square root of 1/4. That one you could have typed in, but since each part was a perfect square, each part of the fraction was a perfect square, it's easy enough to do it in your head, right? Never a bad idea, at least in the beginning of the course, to have a little running list of perfect squares, maybe in the front of your packet, especially if it's something that you're not overly comfortable with. I'll give you the first 10. So, perfect square. So that's 7, 8, 9, and 81, I think. Yeah. You're basically just taking the numbers 1 through 10 and multiplying them by themselves. All right. But if you have those in your mind, then when you come across a perfect square, you can see it as something that's not really challenging. All right. All right, so this guy here, yeah, it looks like a fraction, but it's 21/3. It's 7. 7, yeah. The square root of 9/16 would be what? 3/4. That's one of those fractions that we know in decimal form without having to put it in the calculator. Right? So the smallest value here is the 0.6, right? What's the next one?
3/4.
The 3/4, but we'll write it in its original form of the square root of 9/16. And then the last one is the 21/3. All right, so not too bad. And again, you probably burned right through this. I mean, most of you were well into the second page when we started going over this. So, you know, this wasn't that bad, but hopefully you picked up a couple of tricks of the trade. Different types of numbers. We're going to be talking about these. I mean, this is something you've definitely seen it before, but I don't know how much you refer to it. We refer to these terms throughout this entire course. All right, so that's good news and bad news. It's like, it's like a new language. You know, I'm telling you that we're going to learn some terms that we're going to use over and over again. And you might reply, well, I guess I better get to know those terms. When do I need to know them by? My answer to that would be, well, tomorrow would be nice. You know, because the sooner you get to know them, the sooner you can understand every sentence that comes out of my mouth. Because I'm going to say, all right, what's going on with this rational number and this irrational number? If you're still translating in your mind, then that could be challenging. So that's kind of like the bad news part of it. But the good news is it's going to be the language of the course. So we're all going to be speaking this language before too long, to the point where it'll be customary. It's not going to be something you're going to be thinking about. You in your small groups will be using these terms without even thinking about it. All right. So, you know, just like when you were growing up, you started off as babies and then toddlers and so on, and you started acquiring language, you don't remember when that happened. You don't remember life without knowing how to speak. Like that's how it will be at the end of this course. You won't remember math class without these terms being in it. All right, so that's the good side of it. All right, it's a little jarring, at least initially. Some of the terms are really nice because they tell us in the term what the definition is, like a counting number, right? Well, it kind of gets the idea across that I'm counting things up. I mean, I wouldn't necessarily expect to count 0 things. So I would start with counting the first thing, then the second thing, then the third thing. All right, so that's my example, my set of examples, number used to count items. So that's pretty straightforward. Whole numbers, that incorporates the value 0. All right, so that one's kind of a little on the annoying side, because whole numbers, okay, when you think of whole numbers, you would think of the 1, 2, 3, 4, 5, but maybe not the 0. So a lot of folks will get the whole numbers confused with the counting numbers, right? The integers incorporate all negative counterparts to the positive whole numbers, right? So integers take the 1, make it -1, the 2, make it -2, and so on. But we're still not incorporating fractions, decimals, and things like that. That comes when we're talking about rational numbers, right? The definition, the textbook definition, a number that can be expressed as a fraction, but another word for fraction. Does anybody know another word for fraction?
Ratio.
Ratio. Kind of like the root of the term that we're defining here. All right, so that helps. So if we're talking about a ratio of 2 numbers, you're talking about a fraction, and then therefore a rational number. And you would say, okay, well, what about whole numbers? Well, you can express a whole number as a ratio. 5 is 10 over 2, right? 5 is 5 over 1. It's still a ratio. Right? If you talk about, I mean, this is a little off topic, but if you talk about odds to win or lose an event, like you have 5 to 1 odds, it's for every one time you win, there's 5 times as you lose, 5 times that you lose. All right, so that's a ratio. That makes sense. The decimal form, you would say, well, what about that? Well, if I take something like 7 over 2, which is a ratio, and put it in decimal form, actually divide it, it would become 3.5. So that follows a set of rules. The only things that don't follow the rules are irrational numbers. Those are the ones that can't be expressed as a fraction. Now, a little trick when it comes to that, because I heard folks defining irrational numbers as numbers that don't repeat and never end as I was walking around, which is good. That's a good working definition, all right? But we also want to be able to verify that something is irrational or rational, all right? Because when it comes to taking the regents, you're going to be given a number, and they're going to say, is it irrational and why? So you have your definition, you're good. It never repeats, never ends. You could go with this definition if you want. That's also good. But this number here, I'm looking at it, yeah, it doesn't look like it repeats, but what if it repeats off screen? There are some decimals, some crazy decimals, that like the first 10 values are completely unique, but then after that, the next 10 values are the same as the first 10 values, and then over and over again. So it's a repeat like, it's above, but the 0.16 with the bar over it, that's showing that the 0.16 repeats. Well, you could have a set of 10 values that repeats over and over again. Maybe it's off screen that it's repeating. We don't know. So if you're not sure, if you look at that, just hit math, try to convert it into fraction form. So math option 1, if it keeps it as a fraction, that's the calculator saying that it can't figure out a fractional equivalent for this decimal. So if you're pretty sure that it's not rational, and then you try this, the calculator is basically saying, I'm pretty sure you're right. All right, so you can conclude on your homework assignment, test, quiz, Regents exam, that it's an irrational number. Now, if you have a decimal like, I'll just make up something, 1.125, all right? It's a decimal that ends, so we know it's going to be rational, all right? But maybe you're a little iffy on the definition. You just want to get it right on the test. Math, enter, enter. It converted it to a fraction, so you know that's a ratio. You know it's a rational number, all right? Then you have a set of real numbers, which is the whole shebang, all right? Rational and irrational numbers. All right, the only thing the set of real numbers does not include would be, you guessed it, the set of non-real numbers. All right, those are the what they call imaginary numbers, if you ever heard of those. Those are the cases where you have a negative under a radical. All right, but I say non-real because if you try to put a negative under a radical in your calculator, it says non-real. It doesn't, depending on the calculator, it might say imaginary answer, but most of your calculators will say non-real answer, all right? I like non-real because if we're defining real numbers and it's saying that that is a non-real number, it's saying it's not a real number. So if a question on a test said, is the following a real number, and that just said it's non-real, then you have your answer, all right? So it's pretty nice, user-friendly, all right? So let's just burn through this true-false stuff. What do we got for rad 2? True, because it is indeed irrational. Is pi irrational?
Yeah.
Indeed. What about radical 3 squared?
Yes.
Yeah.
Irrational?
False.
False. Now the radical 3, sure, but when you square it, yeah. Okay, let me actually talk about that real quick, because there's two ways to think about that kind of problem. Radical 3 squared, you could think of it as radical 3 times radical 3. When you multiply two rads, you just multiply, they call them radicands. We'll talk about that more later in the course, but you multiply the two things under the radicals, all right? And so that's going to give you radical 9. Square root of 9 is 3. All right, so that's a rational number. Also, nifty little shortcut. You've heard of canceling before, right? Yeah, it's just like a catch-all term for like pretty much everything in math. But basically, opposite operations cancel each other, right? Addition cancels, subtraction, multiplication, and division. So square root and a power, or a power of 2, which is a square. Those are opposite operations. They cancel each other. So it gives us just a boom, a number 3 right there. Okay, so either way. Worst case scenario, you type that bad boy in your calculator, hit enter, and see what number comes up. All right, the number 3 will come up, and you'll be happy that you did it. Integers are rational. Yep. All rational numbers are integers. False. 0.123 repeated is irrational. It repeats, right?
Yeah.
So that would be, it would be rational, because we can make a fraction out of that. Okay. Root 144, irrational? False. How about 3 squared times pi over 2, irrational?
True.
True. Because of that bad boy right there. Now, don't just assume because pi is in it that it has to be irrational. But most of the time, that's going to be the case. Because pi is irrational. It's going to, if it's multiplied or divided by other rational numbers, it's still going to remain irrational. All right? But if there was a pi on the bottom of the fraction, they would cancel out and it would be irrelevant. So just be careful of like little trick questions. 0 is irrational.
False.
False. All decimals are rational. False. Yeah, we had a bunch of cases where we showed that that was not true. So anything where a radical gives us a decimal is going to be an irrational number. Okay,